Hey Chem fam, I'm Chelsea here to make tricky chemistry concepts simple and relatable for you all. Today we are going to discuss about quantum numbers. Quantum numbers seem difficult not because they are actually difficult, but because they are taught as definitions to memorize. They are not definitions, they are tools. So today, let's break quantum numbers down and understand what they really are and why do we even need them. Once you understand the purpose, tackling questions becomes much easier. So let's start with a question. How do we describe an electron completely? We cannot fix a circular path for an electron like that of a planet around the sun. So, instead of a path, to describe an electron, we use a set of numbers. Each quantum number answers a specific question about the electron. So, one electron needs multiple labels. So the first thing that we want to know is the energy of the electron or how far it is from the nucleus. This information is given by principal quantum number, which is represented by n. So it tells us about the energy and the size, that is basically how far it is from the nucleus. So each value of n corresponds to a shell. For example, when n is equals to 1 corresponds to K shell. When n is equals to 2, it corresponds to L shell, and so on. So different value of n means different energies. So when an electron jumps between these energies or these shells, we observe spectral lines. When we say electron jumps between shells, it does not mean the electron travels through space like a particle. It means electron changes its energy state from one allowed energy state to another, and its wave pattern changes accordingly. So the word jump is just for convenience to describe this transition. Even in textbook, you will often read electron jumps between shells. It does not literally mean the physical jump, okay? So what it actually means is electron changes its energy state and the wave pattern changes accordingly. Knowing the shell alone is not enough. Even within the same shell, electron can be present in regions of different shapes. So the shape of the region where an electron is most likely found is described by a new quantum number known as azimuthal quantum number. So now we will discuss about azimuthal quantum number. Azimuthal quantum number, which is represented by L. So it talks about shape of. So the subshell arises because of this quantum number. The subshells within the shell arises because of azimuthal quantum number. You will understand better. Let's take example. So when the value of L will be equals to 0, it corresponds to S subshell. So the shape of the orbitals within the S subshell will be spherical. When L is equals to 1, corresponds to P subshell. So the orbitals within the P subshell will have dumbbell shape. When L is equals to 2, corresponds to P subshell. So the shape will be double dumbbell and so on. Okay. So for a given shell, the possible shapes depends upon the value of n, the detail of which we will discuss towards the end of the video. Now, there's a question. If two orbitals have same shape, can they still be different? The answer is yes, in their orientation in space. So the orientation of an orbital is described by a new quantum number known as magnetic quantum number. Now we are going to discuss about magnetic quantum number. This is our third quantum number, right? This magnetic quantum number, which is represented by ml, which describes orientation of orbital. So here we will take a simple example. You remember P subshell, right? So this was for L equals to 1. Okay. So now based on L, ml can have certain number of values. Okay. So I'll just write the possible values for ml here. Okay. So how and when and the limits we will discuss towards the end, that will be better. So just for time being, you consider this. So when L is equals to 0, okay, so the possible ml values are -1, 0, and 1, which means that P subshell will have 3 p orbitals. So how do these 3 p orbitals differ? So you see the, what to say, mm, they all have the same shape, that is dumbbell. Then how do we differentiate them? Based on their orientation in space. So the 3 p orbitals will be different based on their different orientation in space. So based on this, the 3 p orbitals are named as px, py, and pz. So how the orientation changes along the different axes in space. Okay, so for your visualization, one will be along the x-axis, oriented in along the x-axis, that is px. Let's say this is px. Another one will be along the y-axis. Okay, this y-axis, this will be py. Then the third axis, z-axis, will be perpendicular to both x and y, right? It's z-axis. So the third one will be along the z-axis, which would be pz. So all the 3 p orbitals have same shape. Okay, but how do they differ? In their orientation in space. One is aligned along the x-axis, another one along the y-axis, and the third one along the z-axis. So for each value of ml, it corresponds to a different orbital. And in the absence, okay, now we have to note something. In absence of magnetic field, okay, in absence of magnetic field, orbitals with different ml values but same principal quantum number and azimuthal quantum number will have same energy. Means when, let's write here, when n is same, l is same, but ml is different. Okay, when m, like different values of ml means different orbitals within this shell of, so within this subshell of this shell. So when n is same, l is same, and you have orbitals with different ml values, when in the absence of magnetic field, all these orbitals will be of same energy, and this is known as degeneracy. Just keep this term in mind. There will be some questions on spectral lines. Okay, so this concept will be used to answer those questions. Okay, by the way, I keep posting shorts with each shorts with one revision question. So if you want, you can of course watch that also for revision. So as I share the topics, the long format explanation topics here, I parallelly do share multiple questions also in the form of shorts, so you can revise it there. Okay, so whenever like I will be discussing some questions based on this topic, the explanation lies here. Okay, so just for your reference, I'm just mentioning it here. All right, so do remember this term degeneracy. So now we just discussed about magnetic quantum number. Okay, and a new term, degeneracy, which will help you in answering questions on spectral lines. All right, now even after fixing the shell, subshell, and orbital, two electrons can be present in the same orbital. So we need one more property to distinguish them, and that is their spin. So that is described by a new quantum number, that the fourth quantum number, that's called spin quantum number. So now we'll discuss about spin quantum number. That's a final quantum number. That's called spin quantum number, and it is represented by ms. All right, which describes the spin of electrons. So this ms can have two values, either plus half or minus half. Now when I say spin, it's actually an intrinsic property of an electron. It does not mean that an electron is physically spinning like a ball. It's basically an intrinsic property, just like the charge of an electron or mass of an electron. All right, so with this we have four set of quantum numbers. Okay, so like this also tells, the spin quantum number also having like either plus half or minus half also helps us to understand that why only two electrons can exist in one orbital, because they should have, in order to have different address of their location. All right, now after discussing all the quantum numbers, let's quickly conclude it in a nutshell. All right, okay, so we started off with principal quantum number represented by n, which represents shells. Then the second one was azimuthal quantum number L, which, which describes subshells. Then we moved on to magnetic quantum number ML, which talks about the orientation of orbitals. And finally, spin quantum number MS, about spin of electron. So this is all that we discussed so far in a nutshell. So this is where many students feel the clarity for the first time. So make note of this. So now that we have understood what each quantum number represents, now let us put everything in a table, not to memorize, but to understand their limits. All right. Okay. So type of information for N, L, ML, and MS. Principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. So under this, first we will discuss what are the values that these quantum numbers can take. All right. So for principal quantum number, it could be 1, 2, 3, and so on, any integer values. All right. Then corresponding to each n value, L can have values from 0 to n minus 1. 0 to n minus 1. So if suppose n is equals to 2, it will be 0, 1. All right. Then corresponding to each L value, ML can have values from minus L, including 0, up to plus L. So if suppose L is say 2, so ML could be minus 2, minus 1, 0, 1, 2. All right. Okay. Then what about MS? Only two possible values, either plus 1 or sorry, plus half or minus half. Then let's see what are the other designations possible. Corresponding to each number, I mentioned the shell names as well. Like if n is equals to 1, it could be K. If n is equals to 2, it will be L, M, and so on. All right. Then what about L? We have already discussed when L is equals to 0 means it corresponds to S subshell. When it is 1, corresponds to P subshell. When it is 2, it corresponds to D subshell. When it is 3, it corresponds to F subshell, and so on. All right. Then when suppose let's take one case over here. If suppose L is equals to 1, that is P subshell, there could be three possible values, isn't it? Minus L, so on till 0 up to plus L. So it will be minus 1, 0, and plus 1. So that will be, it's okay. So when L is equals to 1 means P subshell. So within P subshell, there will be 3 P orbitals. What are those? Px, Py, and Pz. How do they differ? In their orientation in space. One is along the x-axis, another one is along the y-axis, then the third one is along the z-axis. Okay, the same thing will be applicable. I mean, like in a similar pattern, you can see in case of D also, F also. Okay, mostly you will be limited up to D, nothing more than that. All right, then okay, in case of spin, we also represent it as this or this, basically arrows pointing in opposite direction. So this table helps you understand the possible limits of this quantum number. Okay, now that we have understood what quantum numbers are, why do we need it, and what all are their limits, I mean the values that it can take, now let's quickly apply it. Okay, so we will do it step by step and kind of make a diagrammatic representation so that it gives you a final what to say, a big picture for the complete understanding of what all we have discussed so far. All right, so here we go. Okay, so here we will be mentioning the shell, then subshell, and orbital. All right, so we will start with the basic. Basic means that is the principal quantum number. What is the least possible number that it can have? 1, right? So when n is equals to 1, it is K shell. All right, so when n is 1, what are the possible values of L? Only 0. So when 0 means it's S subshell. So this will be 1 is subshell. Now here L is what? 0. When L is 0, what are the possible values of ML? Only 0. So within 1s subshell, we will have 1, 1s orbital. All right. Now, what is the next value of n that's possible? 2 corresponds to L shell. All right. When n is equals to 2, what are the possible values of L? 0 and 1. Okay. There are two possible values, 0 and 1, isn't it? When L is 0, that means it's S subshell. So it is L is equals to 0. Okay. So that means 2s subshell. And when L is equals to 1, it corresponds to P, right? So it will be 2P subshell. Now we'll take case by case. When L is 0, what are the possible values of ML? Only one value, 0. So within 2S subshell, there will be 1 2S orbital. Alright. Now when L is equals to 1, what are the possible values of ML? It's -1, 0, and +1. So within 2P subshell, there are 3 2P orbital. 3 2P orbital. What are those? 2Px, 2Py, 2Pz. How do they differ? They differ in their spatial orientation. Now, when n is equals to 3, that means M shell. When n is 3, what are the possible values of L? 0, 1, 2, right? So when L is equals to 1, that means it's S subshell. So it will be 3S subshell. When n is equals to, so this is L is equals to 0. When L is equals to 1, that means P, right? So it will be 3P subshell. And when L is equals to 2, that means it is 3D subshell. All right. Now, when L is equals to 0, what are the possible values of ML? Only 0, just 1. So within 3S subshell, there is 1 3S orbital. All right. Now, when L is equals to 1, what are the possible ML values? -1, 0, and +1. So within 3P subshell, there are 3P orbital. What are those? 3Px, 3Py, and 3Pz. Now, when L is equals to 2, what are the possible ML values? -2, -1, 0, +1, and +2. So how many values are there? 5 values are there. So within 3D subshell, there are 1, 2, 3, 4, 5. 5 3D orbital. What are those? 3DXY, 3DYZ, 3DXZ, 3DX square minus y square, and 3D z square. So this is this or what to say, this diagram represents everything that we have discussed so far. So take your time with this topic, and once you understand the logic, solving questions from this topic will be much easy for you. All right. And I would just like to let you know that if from the coming academic year, if you are joining class 12 and if you want concept-based chemistry, I'll be starting offline classes in Kottayam, Kerala, and online classes for students from anywhere else. So for details, you can check the comments. So I hope this video was helpful for you all. So thank you for watching, and see you in the next video.